This is the world's most advanced processor. In entertainment, its rendering speeds render other processors obsolete. It drives the future of autonomous driving, powers cloud services for billions, helps change the course of climate change, connects communities of gamers anytime, anywhere, and uses AI to accelerate disease detection and cures. We make the world's most advanced processors, but only with your vision can we advance the world. AMD, together we advance.
Okay, well, good morning, everyone. And thank you for the nice introduction. I must say, normally Mark Papermaster was going to be here today, and he sends his apologies. Actually, he called me up on Sunday evening, that some unexpected event made him not capable of coming here. So I hope I can live up to the expectations of the audience. Perhaps I should say first a little bit about my background. I graduated from the University of Leuven, which is actually the second oldest university in the world after Florence in Italy. So I did electrical engineering, and then I joined a research institute in Belgium, started a couple of companies, was recruited to Silicon Valley to become the CTO of a company which has an unpronounceable name. It was Xilinx. And then a couple of months ago, we were acquired by AMD, which was the largest acquisition in semiconductor history. And so here I am now representing the work and the vision of AMD. It's a very exciting times, as I hope I can share that with you. And actually, this is my first external presentation as an AMD representative. So I will definitely remember this presentation for the future. And of course, joining AMD was a great event for us. We were very excited about that, and now we are really at the heart, of what's happening in the world of computing, right? So we see, without any doubt, probably the most explosive demand of compute performance coming towards us, and we in AMD are kind of this gear in the gearbox, and without that gear, the whole machinery, cannot work. If that gear is not there, the whole thing breaks. And so we are at the heart of enabling this explosive demand for compute performance. One of the things, of course, that, and I don't think that is anything new for this audience that is driving this, is the tremendous demand for compute driven by AI. If I look at, the pace in how AI algorithms and applications and capabilities are evolving in a matter of months, it's unbelievable, right? So if you look at some of these transformer models that are being used for natural language processing and similar applications, you literally see, billions, trillions of parameters that drive these algorithms, and so it's all about the data, right? I mean, I think I read once that by 2030, if we keep on collecting and storing the data that all the sensors and systems that we have worldwide and that we are developing, it keeps on increasing at the same pace, we probably have not enough silicon manufacturing capabilities to just store the data, not alone to process it. So clearly, AI is driving data consumption, is driving, the compute requirements, and it's definitely not a kind of a one-off thing. It's there to stay, and it's continuously increasing, and we clearly are up to the task to support and to provide the necessary technology to enable that. When you look at our roadmaps, we are building the systems now. We are at the heart of the systems that now provide you with exascale computing, right? There's been a tremendous evolution. I think a couple of months ago, we announced the first supercomputer that delivers more than an exaflop. So it's the most powerful supercomputer in the world. It's also the most power efficient supercomputer in the world, because another challenge that we are facing in the semiconductor world is we can keep on increasing and provisioning more and more compute power, but more and more we are being constrained by the actual power consumption of these systems. And more people start really focusing not such only about on compute performance, but on compute performance per watt, because that becomes the limiting factor, not only from what physically you can achieve, but also what financially you can afford. Power and electricity becomes a major operating cost of a high-performance compute center, and therefore, compute per watt becomes really important. So we announced the installment of the Frontier system a couple of months ago. We also announced that we are working on installing El Capitan, which is another factor of 2 increase in performance. So I think this kind of rat race, I would say, continues for the foreseeable future. You might, if some of you are following what's going on in the semiconductor world, you might have heard about people talking about Moore's law is slowing down, and how is that going to reflect in the capability of continuing to improve compute performance. The fact is that the specifics of Moore's law, which is kind of a transistor is getting smaller, and therefore you can get more transistors and more performance in a chip. That aspect is indeed slowing down, but there's so much creativity and options that allow us to continue to go on that road in delivering more performance per watt, that at least for the foreseeable future, I expect that this continuous increase of delivering more performance to computer scientists and so on will continue. Now, the flagship that in AMD that enables this kind of fastest HPC system in the world is our Instinct accelerator. So when you think about the workhorse, of course, of computing is the CPU, right? Everyone is familiar with that, from the laptops to these high-performance systems. The next step we did in order to deliver, the compute performance is starting to add accelerators to the CPUs, and today we refer to it as heterogeneous computing, where, you offload certain tasks to these accelerators, and the root of a lot of these accelerators was in GPUs. I have a hard time still calling this a GPU. This is really a massive multi-core, literally thousands of processing cores, not the cores as you're familiar with in the x86 architecture, but definitely thousands and thousands of micro engines that execute parallel tasks, that have their origin definitely in the GPU architecture. On the AMD side, we refer to this product line as the Instinct product line, and the latest version of that is the MI250X, which is in these high-end compute systems. And in the last from about 2015 to 2020, in AMD we were able to deliver effective compute performance increase in these 5 years of about a factor of 30. And then 2020, we made a statement that by 2025, we want to repeat that. We want to be able to improve the compute efficiency of the systems with another factor of 30. And we are well on track to deliver that, and we are close to, since 2020, we have improved the compute per watt with a factor of 7. And as I said, I start referring to compute per watt because it's actually, the power consumption that limits how much compute you can pack in a certain setting in a certain volume, and that becomes really the key figure of merit for these systems. So we have been doing this. We have been in the last couple of years, in the last 2 years, increased the performance per watt with 6.8 to be correct, and we are well on our way to 3 years from now to achieve that 30 times improvement in performance per watt. Now, for an engineer, it's really exciting times now because in the past, being in the semiconductor industry was actually kind of boring to a certain extent. It probably would not do justice to all the creativity that people did over the years, but to a certain extent, what you did in the past is you had a certain compute architecture, and you waited until the next manufacturing node came along, and you had another factor of 2 performance per watt benefit by just taking that architecture and manufacturing in the next advanced manufacturing node where the transistors were smaller, where the transistors were more efficient. As Moore's law is slowing down, if we want to continue at that pace, we needed to start becoming more creative. And that, for me, as a CTO of the company, is really exciting because suddenly all the ideas that in the past, were kind of put on the shelf because it was just easier to take whatever you had, and move it to the next manufacturing node. Now suddenly people were looking for help to find new ways in how they could continue to deliver that performance. And that led to, for example, the emergence of new architectures. I'll say a little bit more about that. So it was not just about take the same architecture and port it. It also led to thinking about new ways of building chips. So one of the great things that very recently happened, and where we in AMD have been playing an industry-leading role, is that, transistors are shrinking, not at a pace anymore as they did in the past. So we, the kind of we exploited the 2 dimensions now. We are reaching level, almost atomic level for a transistor, and so it doesn't go that further anymore. So we start adding the 3rd dimension. So we're starting now thinking about building chips in 3 dimensions, not just in 2 dimensions, but just add another dimension that gave us a whole new opportunity to start thinking about how we could deliver this performance if we had this extra dimension. Now, that implied that we had to completely rethink how we were building these chips and how we would build these architectures, because this was completely new parameter now, literally a new dimension that you added, a new degree of freedom that you added in terms of how you could build your chips. And that was, for example, a great opportunity and a breakout in our industry. And we are just, by the way, at the beginning of that. So sometimes, problems create new opportunities. And I think it never has been such an exciting time in the semiconductor industry if you are interested in, bringing in new ideas and be creative and so on. And that's what is going to get us to continue to improve that performance that you all have been witnessing over the past. Now, as I said, AMD is definitely considering high-performance computing, and I mean that in the broad sense. I mean, I consider AI definitely also as high-performance computing. We are definitely seeing that, we are, as I said, one of the cornerstone of this technology, and we want to enable, creative thinking, at universities. And for that reason, we also have created what we refer to as a high-performance compute fund. We started that during the COVID days where, we really saw the need for people to leverage high-performance computing to solve some of the challenges in our healthcare and medical system. And we are now continuing at this space and providing support to universities to enable to continue their innovative work in progressing many good causes, be it in the medical field, be it in climate change solutions and so on. I would definitely encourage everyone to have a look at AMD's webpage in what are the possibilities. And this is not just by providing you, access to high-performance compute infrastructure and hardware. We also have a program which we refer to as the HAC program, which stands for Heterogeneous Accelerated Compute Clusters. And one of the things that we believe is going to be important in the future is that when you think about building a high-performance compute solution, you really have to look at a holistic way at the problem. You have to look at it from an application, software, hardware perspective, and not just hardware in terms of what are the chips you're using, but also what is the overall system that you're building. And so, for example, the HAC program provides capabilities to universities to kind of tinker around, with their HPC infrastructure. Literally, you're messing up your networking and you're taking over the hardware, for a while, and you're looking at how the connectivity can be reprogrammed for a certain application, and then you basically give back the hardware to the community. The basic infrastructure is installed again, and somebody else can take over and can play with configuring the hardware to the extent that they deem suited for their application. So it actually gives you an extra degree of freedom, I would say, in terms of solving your problem. It's not just a matter of the algorithms and so on, but it's also about what if I have that extra degree of freedom that I can really tinker with my total architecture of my infrastructure. So that's we are trying to enabling a lot of that research also in the community, in the academic community, and we are definitely would invite the Purdue students and academics to try to leverage that as much as possible. Now, we are here, of course, to kind of also celebrate the Anvil supercomputer achievement, which is quite, an impressive installation. I don't know, I just came in from the airport, so I didn't hear the previous presentation, but and I don't know whether some of the things that already shared, but I think it's definitely one of the top supercomputers in the US for sure. I think it's in the top 200 supercomputers. We are very proud that we can enable this kind of technology with providing I think more than 1,000 compute nodes that are leveraging the latest AMD CPUs and so on. And if I'm correct, there is a little video on this initiative. So if we can have a look at that, perhaps.
The research my group is doing at Purdue is first and foremost build innovative cyber infrastructure. We also bridge the scientific research with the latest technology. So I'm really excited to talk about Anvil, our latest and largest supercomputer on campus. Reach of Anvil is really broad. We're anticipating supporting thousands of researchers to do computation on Anvil.
When we made the decision to go with AMD EPYC, we saw a staggering increase in capability from previous processors. We saw a 45% increase in flops, which is the amount of computations that one can get done over a period of time compared to previous generations of processors. During the course of our testing of the AMD EPYC processors on Anvil, we found that our scientific applications got anywhere from 9 to 30% more performance than previous generations. With the PowerEdge servers in the AMD EPYC processors, we were able to maximize our compute density and get 512 compute cores in just 2U of rack space.
Technology partners such as Dell, Microsoft, and AMD are vital to our success here at Purdue, from an innovation standpoint by creating new products and advancements in technology, and also from a support standpoint, as this is a mission-critical infrastructure and needs to be operable around the clock.
Microsoft Azure was really instrumental in helping us benchmark our applications for the AMD third-generation EPYC processors. We were able to use the virtual machines in Microsoft Azure to both compare the performance as well as port our scientific applications to these processors, which really helped us ramp up our deployment process.
Okay, so quite an achievement, I think, and actually, I was looking here at the exact number. This computer is, it seems like number 143 in the world. In the top 500 computers, the number 7 academic system in the US. So definitely, a very impressive infrastructure that's made available to the students and to the academics and so on. Very, very impressive. Now, as I said, being a semiconductor company, of course, I have to say a little bit about what's under the hood of all of this. And it was already shown in the video, of course, the workhorse of, the technology that we provide for high-performance computing is the CPUs, which today, I mean, are our EPIC CPUs, which are clearly the industry-leading CPUs in terms of performance, in terms of performance per watt. And these CPUs, for example, are leveraging for already the 3D capabilities that I was referring to, and how to kind of get beyond the fact that transistors don't scale that fast anymore and don't get that much of return anymore. These CPUs are definitely introducing that technology, and we're the first in the industry to introduce that capability. Now, the second, technology that I'm sure you all have heard to is, as I said, the MI250, which are the kind of the childs of the GPUs, and in general, people refer to this architecture still as the GPU architecture. Also, these are today based on 3D technology, and you see different dies that are stacked together, memory that is stacked together. So to give you an idea, one die in the GPU in the MI250, that's a compute die, has about 29 billion transistors on there. So there are 2 of them in there, and then you have a boatload of 3D stacked memory. Also there, to give you an idea, the bandwidth between the compute, because if you improve the compute, you have to feed the beast, right? You have to keep feeding it with data to do the compute on. Today, in the MI250, we have more than 3 terabytes per second of memory bandwidth, so data that is flowing into the compute now. Just to give you an idea, 1 terabyte is probably about anywhere between 400 to 500 movies on Netflix, right? So in this one single chip, you're feeding it with about more than 3 terabytes per second of data. So you can just imagine what a massive amount of processing and data movement that is happening. And then other technologies, and that's one of the reasons also why so my previous company, Xilinx, became part of AMD, is as we are continuing to deliver more and more compute performance, we need to get more and more creative, and we need to come up with new architectures, and that's where what we refer to as the XDNA technology comes from. It's the technology that was coming through the Xilinx acquisition, where whole new architectures are now made available that deal with the processing of AI algorithms, which have a very unique characteristic in terms of how you're processing the data. AI is all about doing compute on a massive amount of data. In the beginning, I showed you this slide about these AI network models that have trillions of parameters in there. So it's all about manipulating the data, and actually the data movement in your system becomes as important as the compute. And so traditional cache-based architectures, as we have been using them for ages in CPUs and GPUs, are starting to fall short of being capable of dealing with the complexity and the performance requirements of moving and manipulating all that data. And the new compute architectures are actually dominated by, I would say, the cleverness in how you manipulate data and how you move data around. And that's what we refer to in AMD as the XDNA technology, and the new architecture, which we refer to as the AI engines, which is basically proliferating through the whole AMD product portfolio. And then another important aspect is that when you look at a little bit from a broader perspective, it's not all about compute, in the data center or in the HPC infrastructure. More and more, compute is also moving to the edge. Because if you think about it, the edge potentially delivers such a tremendous amount of opportunities. I mean, you have out there millions of endpoints out, in the infrastructure, enabled by IoT capabilities and so on. Whereas all these endpoints might not be necessarily the most powerful compute engines, if you look at the aggregate, they're delivering an order of magnitude, if not more, compute capabilities to a total solution than just a basic centralized infrastructure. And you see more and more that people start thinking, when they start about complex compute, they start thinking about the combination of what we refer to as the edge compute, the endpoints, together with the compute in the data center. A good example, for example, is federated learning, as we refer to, where in a traditional AI environment, what happens is, okay, you have a problem statement, you define an algorithm, a neural network for that. You collect an immense amount of data. You're training in your HPC infrastructure, you're training your neural network, and then you're deploying that neural network. We refer to that as inference, somewhere in mundane applications at the endpoints and so on. Now, training is, of course, a tremendously compute-intensive aspect, and needs to be constantly updated and redone, and literally it can take weeks of compute time to get some of these complex networks to kind of get acceptable results and be trained well. But if you think about federated learning, the idea of federated learning is that you have all these individual nodes, and it could be millions of them, right, or even billions of them, that deploy an AI application in the node and find potential problems where the AI doesn't really give the answer that is correct. And the endpoint can correct that, can adapt the parameters, and can then, rather than sending all this data to the central point, can just send the adapted parameters to the central point. Central point collecting all these parameters and is then updating the network model and is sending it, distributing it again, through all the endpoints. That's kind of federated learning. And so what you see is that you need capabilities at the endpoint that are more powerful than what we're typically used to, that have similar characteristics than what you see in the central compute, but that can be deployed in an endpoint in a more power efficient way and not necessarily have to be that performant as in the HPC center. And that's what we refer to as adaptive SoCs. That's also one of the technologies that the acquisition of the Xilinx technology brought to AMD. And of course, the obvious places where you see that being deployed is like in automotive and things like that, where more and more people start improving the cars, and that one day hope, we really get these autonomous vehicles being everywhere around us and so on. And so that's, now these compute architectures also need to have some extra characteristics. When you do a traditional application in software, you can, I'm using, when you open up something in Windows and you open up your PowerPoint or something like that, it doesn't behave all the time at the same way. Sometimes you open up PowerPoint and bang, your slide is there. Sometimes you see this little circle, going and going, and it's not always predictable what's going on. Now, when you're in a car and you push the brake, and the brake is causing, a software program to tell your brakes to basically activate, you definitely want to have a pretty deterministic behavior, which implies that you need another kind of computer architecture to handle that than a computer architecture that would do your Word application or some offline application. So determinism and real-time architectures are becoming also important when you look at the total solution that you're trying to look at. That's what these adaptive SoCs are delivering. And then finally, I already said it's all about more and more about data movement. So when you build a system, you have to start realizing that what we see, for example, in data centers and so on, is that I would say perhaps, I don't know, I'm just making an educated guess here, but I wouldn't be surprised that about half of the cost of the data center has to do with infrastructure to move the data around, not necessarily to compute, but to move it around, right? And to do that in a most efficient way. And that's where network interfaces become important. These network interfaces are no longer, traditional static kind of infrastructures. You're going to program how your data is moving around in your HPC infrastructure, tailored towards the problem you're trying to solve. So you do not only program with your application, your compute nodes, you also program how the data is moving around and how the connectivity is implemented and what is the protocol that you're using. Are you using large packets, small packets, how do you organize that to do this so efficiently as possible? Because a lot of the power and the time and the resources go into moving data around because a lot of these algorithms are data intensive. So smart NICs are becoming really important. These are network cards. In the past, you didn't think too much about it. You had these network cards sitting in there. Now, these days, we refer to them as smart NICs, where the reason is because as a software person, you can program them to kind of be tailored towards your application. So you do not only program the compute, you also program the data movement. So all these technologies now, we are optimizing in a holistic way in AMD. So we have access. I think we probably are also the only company that has all that plethora. We have started with CPUs, added GPUs, added AI compute, and then finally, most recently, we added the networking, programmable networking capabilities to provide that total solution so that you have all the tools in the toolbox to build the optimal compute infrastructure. So that's a little bit what we are doing in AMD and what technology we are working on to enable many of you to do your job in as efficient way as possible and solve the big problems of society like climate change and healthcare and bioinformatics and so on. And of course, you cannot do that without the engineering smartness, I would say, that then makes creative use of this technology, right? And so I was asked also to say a little bit more about that and why engineering is important. And one of the things that I typically when I talk to university now, in this case I probably have an audience that is already convinced that engineering is important, but I think engineering is actually a fantastic career choice if you think about it. And I once had to give a presentation to a university. I was a broader group and explaining why they should go for engineering and so on. And one of the things I did was I looked at, and it's a couple of years ago, I looked at statistics of the, what is it, the Bureau of Labor Statistics or something like that, one of these government agencies. And I looked at how many professional athletes there are in the US. And at that time, there were I mean, I think guys like LeBron James or Tiger Woods or things like that, if I say professional athletes, that's what you're thinking about. Well, at that time in the statistics, it said there were about 14,000 professional registered athletes in the US. And their average pay was $40,000 per year. Then I looked at professional actors. And there were more, actually. There were about 70,000 professional actors in the US. And their average pay was $20 an hour. And then I looked at how many computer scientists there were. And that was about 1.5 million. And their average pay was $100,000. And then you had electrical engineers, and you had mechanical engineers, and you had chemical engineers, and you had bioengineers, and they all were in the hundreds of thousands and so on. So first of all, engineering is a profession, I think, that gives you so many opportunities. And sometimes young people are having this image of, you know, they see these people on TV and the sports events, and they're dreaming. And I'm coming from Europe. I'm always impressed about, you know, how much the university is paying attention to athletics and things like that, which is definitely good. But they should do the same kind of events, I would say, around engineering, in all fairness, because there's a lot of opportunities in that. And I think when you go for an engineering profession, there are so many aspects and so many choices you have. First of all, I think as an engineer, you can be a sales engineer, you can be a market engineer, you can be a development engineer. I mean, depending on where your preferences are, there's so much that you know you can choose, I would say, that is mapping what your skill sets are, what your priorities are. Of course, a lot of that is rooted in certain basic capabilities that you need to develop and need to deploy. And, you know, I told you guys, like, our chips are, 29 billion transistors on one single die. Well, you know, if you design something like that, you have to be able to abstract a little bit the complexity of that system, because if you stare at 29 billion transistors and they all have to work, you know, it's definitely not going to be a story with a good ending. So you really need to be able to abstract. You also need to, you know, be kind of wondering, you know, in how things are working and how you can improve things. I think you also need to have an attitude that you sometimes go into a territory that you're not familiar with, and you kind of say, okay, I'm going to do this. An engineer is, I would say, is typically somebody who's creating a good path, not necessarily paving the path, but creating the path. And I think that's, I believe, an attitude that's really important. I remember when I came to the US, I started as a research engineer, did my PhD, went in the research institute. I actually started 3 startup companies. One of these companies had the CEO of Xilinx on the board. And you know, when the company got sold, he kind of called me and he said, I want you to become CTO of Xilinx. First of all, I had never worked in the US. The biggest company I had run was about 20 people. And Xilinx at the time was, you know, a 3,000 people company. And they were working on something like FPGAs, which are these programmable chips I was talking about. They are much more powerful than CPUs and GPUs, but they are tremendously hard to program. I was really not a specialist for that. And I was like, I used them, but I was not a specialist. And I told the CEO at the time, I said, you realize that, I'm not a specialist, and you want me to run the research? I mean, that's kind of like, And he said to me, you know what? If I need a specialist about FPGA, I have 2,000 people I can ask. That's not what I want. I want somebody who kind of does new things. And, very little heart, very scared. I moved to the US, took my family with me, and I think the rest is history. Another important aspect that a lot of engineers, I think, need to have a skill set for is be able to communicate, what you're doing, what you're trying to achieve, and so on. I see so often people trying to explain, to management what they're doing, but they're going into the technical details. They're losing the people, their audience, and they're missing the point, and they don't get the traction with their ideas. So really having empathy for the audience that you're talking to is another important characteristic, I think, that I felt helped me a lot, I think, in my career. And then, of course, interesting enough, I started my career about 40 years ago. And believe it or not, I did my PhD on AI. And then I stopped talking about it because I felt people would have thought that I was really a stupid guy to work on AI at the time. What happened then was what we call as the AI winter, right? I mean, for decades, it was not a good thing to talk about AI. And I moved into, device physics, transistors. Then I got lured into more software because I started integrating ARM processors in the chips I was building and became more a software person. And slowly but surely, I'm back into AI now. So it's really interesting to see how if you think you're in a certain domain, during your career, there's so many different paths you're taking, and you should take them. In my case, I ended up, where I started to a certain extent, which is it's an interesting route. And then another important aspect is that as an engineer, and that's another thing I see, sometimes we are, pretty individualistic, and the typical image of an engineer is the introvert nerd, and so, and that's not, I think, a correct image. I heard once the joke is that an extrovert engineer is somebody who's watching the shoes of the other person. That's the wrong image of an engineer. Engineers should be able to work together in a team, to contribute. It's like, think about the symphony, right? There is one composer of a symphony, but you cannot enjoy the symphony if you don't have the orchestra that plays it. And so that's what the engineers are. They are the orchestra. They are basically making, the smart ideas available and make them reality, for a broader group of people to be able to use them. So I think a lot of that I found back in AMD, and I just, as a final thing of my presentation, wanted to say a little bit of a pitch for AMD. I think we are, of course, one of the fastest growing semiconductor companies. We bring a lot of people on board. We have definitely an engineering culture. The majority of our employees are engineers. Interesting enough, it's a whole blend of engineers. You would think semiconductor engineer, semiconductor, that's electrical engineering. Well, majority are computer scientists. We have a lot of mechanical engineers because building a package, for these chips and building 3D structures that are chips that are stacked on top of each other is pretty darn difficult from a mechanical point of view. Thermal behavior of your system, really important to understand that. chemical engineers, right? The materials that we are using, the interaction of the materials that we're using to build these chips, very complex. So there is basically such a multidisciplinary group of people that are working together. And, so that's kind of the environment we are in AMD. And so we have this very multidisciplinary, very exciting culture. And culture is something which is unique for a company. And it's really, everybody is probably talking about culture, but culture is really something that's very hard to change. The culture of a company is good or it's bad. And because culture is something what people do when you don't watch them, And so therefore it's very difficult to kind of, from a management perspective, say, that's the culture of the company. I think you have to live it, you have to demonstrate it. And I think if I look at the AMD team, we showed these cultural benefits every day in terms of transparency, problem solving, decision making, risk taking. It's all important. And so this is also an open call. I mean, if there are students in the room, internships, we are always open for internships. It's a great way to kind of get a little bit of a feel about what engineering is all about, and kind of get a little bit more insights about what are the expectations of a job moving forward. So finally, I would like to say that it's a great moment to be an engineer these days. There's a lot of people that are looking at the potholes of the technology, but these create a lot of opportunities for us. And it's a great moment to be creative. New ideas are accepted with open arms. We are, as I said, the gear in the gearbox of the future, and especially when we talk about compute and AI. And there's a constant capability to learn new things in our industry. So I would encourage all of you to continue, and hopefully you will be successful and end up in this industry. So thank you.
So we have time for maybe one or two questions. Any questions? Kevin.
So you mentioned efficiency several times. I think the center for efficiency. And you also talked about going 3D. And you actually mentioned it right at the end there that as you try to do those things, you have thermal implication. Is AMD looking at the energy efficiency of the whole system, or just focused on the electrical efficiency of the device?
No, I think we are basically looking at the efficiency from the supply chain to ultimately the software that is running on the infrastructure that we are enabling. So we have kind of an ecosystem, I would say, where we're working with partners of the whole food chain. And as I said, yeah, we are a little gear in that gearbox. But if you don't look at the total, end-to-end solution, I think you might miss where the biggest opportunities are, to gain the benefits of the performance. And as I said, right, one of the things why we have now also in our product portfolio, it's not just about compute anymore. It's about, it's also about the networking, and it's about, how you build the overall system. And then we also work with our suppliers in terms of what are the materials that are being used, and what materials are, more effective and more efficient than other materials, and we will encourage our suppliers to, go with these materials and so on. So it's really end-to-end that we are looking into this.
Do I see another question? You have to yell.
There was-
Good morning. My name is Feng Dash, and I'm a PhD student studying computer architecture. My question is about the code chain for programming the XDNA architecture. Do you envision this code chain to be closed source as the Xilinx code chain for FPGAs, or do you envision it to become open source?
Yeah. Thanks, that's an excellent question. So one of my responsibilities actually in AMD is running the open source office, and it's a new initiative. I'm a very big advocate of open source, let me say that, and I'm every day kind of pounding that, that case in the company. I even was that when we were in Xilinx actually, and I took that with me because ultimately the software is what enables and unleashes the full potential of our hardware that we are building. And the more people are tuning into this and helping, you know, to make this more efficient, the better. So open source is an enabler for creating an ecosystem and creating an incentive for a broader community to look in how you unleash that full potential of that hardware, in my opinion, is important. Now, to answer your question about what kind of software, is it going to be like the Xilinx software? I would say no, because the Xilinx software, it seems like you're familiar with this, comes out of the world of hardware design, right? It's kind of, you know, HDL, or in best cases, some C programming or so. We are heavily working with like the MLIR community and so on to really build on top of that standardization and that ecosystem to build a tool flow that kind of is much more bridging the gap with the you know, computer scientists who do not want to be exposed to all the complexities you know, of the hardware, right? So that's the direction that we are going. And very specifically, for example, MLIR is very important for us.
All right. Unfortunately, that's all the time we have today with Ivo. Let's thank our speaker.
Thank you.
Thank you so much.
Thank you.